Greetings, John Lighton here. I'm going to tell you about our Promethion multiplex systems and how they actually, counterintuitively, give better temporal resolution than legacy continuous systems. So we'll be talking here about measuring the fire of life, which is a poetic way of saying measuring metabolic rates, or energy expenditures. And because we'll be dealing over here with experimental animals, we want to do that with the highest possible temporal resolution because they can shift and change their metabolic rates very rapidly. Now, my qualifications for sounding off on this subject. I'm a recovering academic. I spent many years doing research on very small animals that required me to develop very, very sensitive gas analysis techniques. I have quite a good number of peer-reviewed publications, including in some good journals. And also have authored the only existing textbook on comprehensive methods of measuring metabolic rates, about which a colleague, Ted Garland at UC Riverside, was kind enough to give me this very glowing quote. Now, moving right along, let's look at how we actually measure metabolic rates. And we're going to be concentrating here on metabolic rates of experimental animals, and particularly small ones such as mice and rats. First of all, you contain the animal in a cage or chamber. You flow air, pushing it or pulling it, through the cage, and the animal, of course, is consuming oxygen and releasing CO2 unless it's dead. So we can now measure those changes that the animal produces in oxygen and CO2, and these changes are called delta O2 and delta CO2. And then we can calculate the metabolic rate and energy expenditure from the flow rate going through the cage and from the delta O2 and delta CO2. So let's just imagine an empty cage. This is a typical Promethion cage right here. And we're flowing air into it, and the oxygen going in is exactly the same as the oxygen coming out. The CO2 going in is the same as the CO2 coming out. And of course the delta O2 and delta CO2s are zero. Now let's repeat this with an animal. Here we put in a mouse. Our old friend the black 6. Oxygen going in is now higher than oxygen going out because the mouse has consumed oxygen. Likewise, CO2 going in is lower than CO2 coming out because the animal has produced CO2, leading to a delta O2 and delta CO2 that are both larger than zero. So let's look at how the old type legacy metabolic phenotyping systems measure metabolic rate. And a lot has to do with the flow rate. The old legacy technologies use slow flow rates of about 0.4 to 0.5 liters per minute. So here we come with a nice slow flow rate. And that gives us a very big delta O2 and delta CO2. Why? Because the very low flow rate has given the animal plenty of opportunity to change the concentration of oxygen and CO2 in the air. The result is that the old technology analyzers, the legacy analyzers, require a big oxygen and CO2 delta. And the reason for that is the high noise levels in these old technology legacy analyzers. So it's okay to have a very large signal delivered by a low flow rate, but it is definitely not okay to have a smaller signal and a higher flow rate, because then the deltas will just disappear in the noise of the analyzer. So what effect does this have? Well, there's a problem that the slow flow rate causes. It will fill the cage very, very slowly. As a consequence, we have to deal with something called the time constant of the cage. Now let me introduce that to you. The time constant is the volume of the cage divided by the rate of flow being pushed or pulled through the cage. Typical example here, about 8 liters STP is the internal volume of a typical home cage for mice. 0.4 liters per minute, typical legacy flow rate, giving you a time constant of 8 over 0.4 or 20 minutes. So, as a side effect of this, if the animal in the cage changes its metabolic rate suddenly, it will take 20 minutes for the instruments connected to the cage to measure just 63% of the change. by which time, of course, the mouse is doing something completely different, and 100 minutes for 99% of that change to be measured, by which time the mouse has been doing dozens of different things. Now, you might wonder where these particular numbers come from, and I would encourage you to read my textbook if you have any questions of this kind, because everything is explained there. The result is that the low flow rate and the high time constant ruin the temporal resolution of the cage, which is now slow and blurred because of the 20-minute time constant, and the restricted maximum change possible per time constant. The result, and this is a subtle point that I will go into in more detail, is sampling from the cage output more than about twice as rapidly as the time constant gives rapidly diminishing returns and soon becomes actually pointless. So let's look at a metabolic signal. And here is one time constant. You can see the metabolic signal does indeed change modestly during that time constant. If we sample that signal once every time constant, we get a fair approximation of what's happening underneath. If we sample twice, we get a better approximation. And if we start sampling more and more frequently, the degree to which the improvement occurs is rapidly diminishing, until very rapidly, basically, you can sample more often, but you're not getting any more information from that waveform because of the slow time constant. So let's model this. Mathematics is the language of science. We're scientists. So let's think. We have this little black 6 mouse, and it changes its energy expenditure like so. Across time, that's minutes along the x-axis. So it has a resting energy expenditure of about 0.3 kcal per hour, and every 30 minutes it abruptly changes its energy expenditure to 0.8 kcal per hour. So now this is the actual metabolic signal, and real mice are capable of changing their metabolic rates almost as rapidly as they do in this mathematical model. Now let's look at what the cage does to this signal. Here's the actual signal. Goes into the cage, and what comes out of the cage is this. With a time constant of 20 minutes, this is what the outgoing gas concentrations look like from which you would calculate energy expenditure. As a result, your energy expenditure does not resemble the actual energy expenditure of the mouse any longer. It's highly distorted. As you can see, every time it becomes active, it slowly begins to climb, and every time it stops being active, it slowly begins to decline. Now, among the most important metabolic parameters that you need to know as a researcher are the resting energy expenditure of the animal and its active energy expenditure, which in this case are 0.3 and 0.8 kcal per hour, respectively. And as you can see, if you look down at the legacy metabolic phenotyping system output, well, where exactly are you measuring active and inactive or resting energy expenditure? There's really nothing there to really give you a guide as to what the resting and active energy expenditures are. So, because of the fact that the signal is blurred so much by the long time constant, sampling more often than about twice per time constant doesn't deliver much new information. And again, that's because of the slow time constant that has diminished the rate of change of the signal to the point where sampling it more rapidly begins to deliver very rapidly diminishing returns. In other words, you could sample it every 5 minutes or every 1 minute, or even every 30 seconds or 1 second, or 1/100th of a second. And it wouldn't actually make any real difference to the waveform that you're looking at right now. So this waveform could come from a continuous legacy system. So another way of looking at this is if we take about a 10-minute section of this legacy system output, it very closely approximates a straight line. And 2 points will define that line, as well as 3 points, as well as 5 points, and as well as 9 points. And as you can see, you can increase that to 600 points, or 1,000 points, or 100,000 points, without really getting any new information. This is a really important point. Now let's look at how things happen with Promethion. We use a very rapid flow rate. The result, of course, is that we have a small delta O2 and delta CO2. Now, we can cope with that because our analyzers have 1/10 of the noise, roughly, of the old technology analyzers used in the legacy systems. So the 5 times smaller delta is no problem. Now, you might think I'm just blowing smoke. Really? 1/10 of the noise? So, I'm going to give you some proof. So here is the proof. This is the world's highest resolution oxygen analyzer currently. It is the Auxilla oxygen analyzer that is capable, in the scientific literature, this has now been proven, of resolving 0.3 parts per million, which is 0.0003%, whereas a legacy analyzer would struggle to resolve better than about 0.01%. This is just one of 8 standalone gas analyzers that are designed and built by Sable Systems. Here are some of the users of these standalone gas analyzers. And I should point out here that NASA is our biggest single customer for our standalone gas analyzers. And they have subjected them to very thorough verification, and they have passed with flying colors. And they're a very, very fussy user, I can tell you. We love them. Now, here's our 5 times higher flow rate. Look, it filled the cage 5 times faster. Now let's repeat our experiment to see the effect of the cage at a higher flow rate, 5 times higher, and you can see we're now looking at something that much more closely resembles the underlying metabolic signal. So we go from this, where basically you just really couldn't tell what was going on in the gas exchange and legacy, in the legacy system, even if it was continuous, simply because of the low time constant. Now we go to this. So equivalently, we can look at resting energy expenditures and active energy expenditures, and we get a pretty good estimate of both active and resting energy expenditures from the system, which is exactly how it was designed. You might want to know how you can improve the bottom trace so that it resembles the top trace more accurately. It is actually possible to do that. I'm not going to go into that in this talk, but if you read my textbook, you'll discover how that can in fact be done. So to recap, this is multiplex data, and we have a good estimate of active energy expenditure and of resting energy expenditure. This is a continuous trace from a legacy metabolic phenotyping system, and as you can see, it gives you a huge underestimate of active energy expenditure, enormous underestimate, and a very strong overestimate of resting energy expenditure. So you might wonder which system is better. Well, I think it's pretty obvious. The Promethion, even if it's multiplexed, because of its rapid time constant and the fact that we can multiplex far more rapidly than other manufacturers can, thanks to our mastery of gas handling and analyzer response, we really get a very, very good temporal resolution from our multiplex systems. Versus a legacy continuous system, you cannot get away from the lower time constant, the low, very, very slow time constant. And it doesn't matter if it's continuous or multiplex, because you'd get no more information, practically speaking, from the continuous system because of the low rate of change of the signal. Now, what about real data, as opposed to mathematical models? Well, here's a fairly low-end legacy metabolic phenotyping system, and as you can see, you really have no information on resting energy expenditure or active energy expenditure, and there's no real detail in the trace. So it's of very little use. What about the higher-end legacy systems? Here's an example. You still have no idea what resting energy expenditure is. You still really have no idea what active energy expenditure is. And the correlation between activity and energy expenditure is very, very poor and inconsistent. Now, that we have shown that the high-end legacy systems, both mathematically modeled and in real life, have poor temporal resolution, let's look at Promethion. This is what a typical Promethion metabolic record looks like. And as you can see, it looks completely different. Notice the very, very good correlation between activity in green and metabolic rate in blue. So we have excellent resolution of resting energy expenditure. There is no need to do the mathematical trickery that is required with legacy systems, where you graph activity along the x-axis and energy expenditure on the y, and then extrapolate back to zero activity and hope that you're somewhere near resting. Here you read it right off the graph because of the high temporal resolution of the system. Likewise, very tight correlation between energy expenditure and activity, again because of the fast time constant. The moment you have cross-bridge cycling because of activity, you have energy demand, you have increased oxygen consumption, CO2 production immediately. There's a beautiful, quick correlation. And this means that you have excellent resolution of active energy expenditure versus activity, and you can determine the precise energy cost of activity. Even, for example, measuring cost of locomotion of mice on a running wheel, inside the cage with no stress. And another small point, you do get accurate RQs. The reasons for that are mostly due to the analyzer accuracy and the better ways we have of gas handling and coping with the dilution effect of water vapor. Here's an actual quote from an ex-legacy system user at an Ivy League university, and he said, "I feel as if the scales have fallen from my eyes, and indeed, when you're used to looking at legacy metabolic phenotyping data and then you look at Promethion metabolic phenotyping data, it is a whole different experience." So, conclusions. The Promethion multiplex system has definitely got better temporal resolution than legacy continuous systems. And this is because of Promethion's much faster time constant, which in turn is enabled by better analyzers and better system design. Now, I should mention as well, we have 400 times the bandwidth of legacy systems. We have 400 times more information being stored per second from a Promethion system than you would get from a typical legacy system. In addition, because of this high bandwidth, we can do really advanced behavior analysis as a standard feature of a Promethion system. That includes time budgets, locomotion budgets, and fairly sophisticated things such as behavioral transition probability, matrices, hierarchical object clustering of various aspects of behavior, Markov chain creation, and what have you. And these are beginning to be used now in the literature and will soon become absolutely an essential. And Sable Promethion is the only system capable of generating these, together with metabolic measurement. Now, primarily the big difference between Promethion and the other systems out there is it is designed by scientists for scientists. We designed Promethion as an absolutely no-compromise tool for discovery for scientists interested in metabolic science and behavior. As such, really, it has no match. Thank you very much for your patience during my presentation. Do visit our website at sablesys.com. If you are courageous enough to follow my personal Twitter, it's at sablesys. And if you would like a PDF of my textbook, just ask. Thank you again for your attention.